Hello everyone, my name is Wang Degang. I'm from Americas. The topic of my presentation is BockNet, Blind Block Reconstruction Network with a guard window for hyperspectral anomaly detection. My presentation will include these 5 parts. First, the background of our research. Second, the proposed method in our paper. Third, experimental results on 4 datasets. And the last, some conclusions and references we have got. Firstly, I would like to introduce the background of our research. Hyperspectral remote sensing images contain rich spatial and spectral features of different ground objects, and each pixel can be described by a continuous spectral curve. Hyperspectral images have been widely used in many fields. In many applications, the hyperspectral anomaly detection can identify anomalous objects that deviate from the background distribution without using any prior information. As shown in the figure, aircraft located at an airport are regarded as anomaly targets, and the spectral curves of the aircraft are significantly different from those of the surrounding ground. Then, the anomaly detector is applied to separate the anomalous targets and the background in the image. So, what are the features of anomaly targets in hyperspectral images? In general, there is no prior information about anomalies, and they are significantly different from the background in spatial and spectral dimensions. Meanwhile, anomalous targets occupy a low proportion of the whole image and have a low occurrence probability. In recent years, deep learning has been widely used in hyperspectral anomaly detection with its powerful feature mining capability. The current mainstream method is based on the background reconstruction model, and the core idea of this group is to reconstruct the background in hyperspectral images well with the help of some advanced networks such as autoencoders, GANs, and blind spot networks, and then separate the anomalous targets from the images effectively. Before describing our method, I will talk about the motivation for using blind spot networks. At the beginning, we added anomalous targets to the noisy images and removed the noise using a traditional denoising model and a blind spot network based on self-supervised learning respectively. We found from the denoising results that the blind spot network could also remove the anomalous targets, which is what we expected to see since the reconstruction area of the anomalies was enlarged in order to facilitate the detection of anomalous targets. So, how do blind spot networks work? The unsupervised models that use traditional convolutional neural networks typically adopt an identity mapping approach, which means that the unsupervised model can see the information of the corresponding pixel when it predicts each pixel. As a result, anomalous pixels can be easily fitted, and such models usually use reconstruction errors to detect anomalies, leading to unsatisfactory results, often because the reconstruction error for anomalies will be as small as the background, and we are hard to distinguish between anomalies and the background. Unlike existing unsupervised models, the blind spot network has a blind spot in the center of the receptive field, promoting the network to reconstruct the blind spot using only its surrounding pixels, avoiding identity mapping of networks. Since the anomalous pixels are significantly different from the surrounding background, the blind spot network fails to reconstruct anomalous pixels well, which leads to a larger reconstruction error of the anomalies. Therefore, the architecture of the blind spot network suits the hyperspectral anomaly detection task quite well. Next, I will show two previous works we did to verify the effectiveness of blind spot networks in hyperspectral anomaly detection. The first work creates blind spots by replacing each pixel by its surrounding neighbors, so that the background reconstruction network predicts the value of each pixel using only its surrounding pixels information. Finally, the entire hyperspectral image is fed into a trained background reconstruction model, which can obtain a pure background image, and the reconstruction error is taken as the final anomaly detection result. Afterwards, we found that the original blind spot network shows excellent performance in the anomaly detection task for small-sized subpixel targets. However, the pixels inside anomalous targets with a certain spatial size have small spectral differences, and therefore the original blind spot network will easily reconstruct the large-sized targets, which increases the probability that anomalies will be predicted and leads to unsatisfactory detection results. To this end, we introduce the pixel shuffle downsampling PD strategy, which breaks the spatial dependency between the pixels inside the anomalous target and spreads the anomalous pixels into different sub-images. It extends the application range of the blind spot architecture, and it is suitable for detecting anomalous targets of different sizes. Specifically, we need to use the PD operation to obtain the shuffled hyperspectral image. At this time, the size of the anomalous target becomes smaller. Then the shuffled hyperspectral image is input into the constructed dilated blind spot network for self-supervised learning, where the dilated blind spot network mainly consists of masked convolution and dilated convolution, and the detailed process can be seen in our paper. It should be noted that the detection phase shows the same behavior as the data processing during the train phase. We input the hyperspectral image into the trained background reconstruction model, which can obtain the pure background image, and takes the reconstruction error as the detection result. Secondly, I would like to introduce the proposed method, blind block network BockNet, in our paper. In order to flexibly detect anomalous targets of large and small sizes in the image, the network embeds a sliding dual-window model to extend the application range of the blind spot network. Specifically, the receptive field of BockNet can be extended in each direction, but does not contain the center block. The center block can be regarded as the guard window, that is the inner window, and the receptive field outside the blind block is regarded as the outer window. Our BockNet only uses the outer window information to reconstruct the center pixel. If the center is anomalous, then there is a high probability that the target is located within the guard window, so that the network is hard to predict the anomalous target, which will lead to an increase in the reconstruction error of the anomaly. The detailed process can be found in our paper. Okay, now we move to the experiments. The first is the considered datasets, which contain anomalous targets of different sizes. Then follows the experimental results, as can be seen from the RLC curves. The right curve of our BockNet is usually located in the upper left kernel, and our BockNet achieves the highest AUC value compared to the other methods. Next, we come to the fourth part, conclusions. Our work paves the way for hyperspectral anomaly detection in a self-supervised learning manner. The architecture of blind spot networks suits the hyperspectral anomaly detection task quite well. The original blind spot network shows excellent detection performance when identifying small-sized subpixel anomalous targets, and BockNet are flexible for identifying both large and small-sized targets. The BockNet works as a sliding dual-window reconstruction model, extending the application range of blind spot models. Now we come to the last part, references. These are the main references mentioned in the presentation. That's all for my presentation. If you have any question, please feel free to contact me. Here is my email address. That's all. Thank you.